could no longer find statistically significant predictors of the independent variable in a unique sense of the dependent variable. Here's a summary table which gives us the R squareds, and we can see that as we go down we get to the last model 5. So it started with a multiple R of 0.73, and then by the end, by including more independent variables, more listed investment companies, it got up to an R of 0.91. That's very high. We got R square of 82.2% of the variability in AFI can be accounted for by the 5 listed investment companies. And then this is the adjusted R square, which is somewhat lower than the original R square because it takes into account sample size, which in multiple regression there is an adjustment that needs to be made to the R squared value to be an accurate representation of the percentage of variance accounted for. Most people rarely report the adjusted. I have to say, you usually see R square, but not adjusted R square. And here are the standard errors, and I'm almost positive these standard errors are associated with R square, not adjusted R square. Not that it would make much difference anyway. Then we've got the Durbin-Watson statistic, which is testing for the hypothesis that there might be a serial correlation in the data. In fact, Durbin-Watson, there is an approach to testing it statistically significantly. You can't do that in SPSS, but there are tables upon which you can use to compare Durbin-Watson. But as a rule of thumb, you can use something like 1.5 to 2.5. If your Durbin-Watson value is within 1.5 to 2.5, you probably don't have meaningful serial correlations. But in this case, we have less than that, so there is a serial correlation. And I'm just going to point that out and not go into much detail about what the implications are of that. I might do one extra thing at the end of the analysis to show this. No, I probably won't. Okay, so here's the Anova. And what the Anova is doing is it's testing the statistical significance of the model at each step, so each sequence. And at the most important one is the 5th one, which includes, as you can see in the bottom here, DJW, ARG, AMH, DUI, CIN. That's for E. So there's a p-value here, p less than 0.001 with an E, and it tells me what independent variables have been included in that model. And then it gives me the F value, 76.57, with degrees of freedom of 5 and 83. Something that people ask about or point out and confused about is that the F value associated with the models usually goes down as you increase the number of independent variables in the model. And people are surprised to see that because the R value is going up, and yet the F value is going down, which suggests that the significance level is also going up. So it's becoming less and less significant. And I can just assure you that this is actually accurate. That's what you expect when you do a multiple regression analysis and you include more and more independent variables into your equation. Typically, by the time you're getting to the bottom, each inclusion of the independent variable is not really adding a lot. It's very small amounts of variance, and when you're adding very small percentages of variance to your regression equation by including a whole extra independent variable, you begin to compromise the trade-off of including extra predicted variance and just extra a re-estimate of the residual variance. So you can see that the regression sums of squares are going down, but the residual is actually going down much more slowly, and so that trade-off, it's a trade-off that you're making. So that's perfectly normal to see that. If you want to get the actual statistical significance, you just have to double-click, and you can get that there. You just have to cell properties. It's probably still going to be very, it might even go beyond. Yeah, so it's very, very statistically similar. I couldn't even get the value. So p less than 0.001. Then we get the table with the actual beta weights. And beta weights and the statistical significance associated with the beta weights. Again, just go to your last model. If you're happy with the model 5 and you I just jumped it there. There we go. So we got the unstandardized beta weights here in the first column. So DJW has an unstandardized beta weight of 0.32, and the intercept, what SPSS calls a constant, this is the intercept associated with the model. And then we've got their unstandardized beta weights here. I'll assume that you already kind of know what a beta weight is, and I'm just going to point out these are the unstandardized beta weights. It corresponds to the